Morning.
Good morning. I'm so happy to be back with all of you. Really sorry about last Thursday.
Well, it was an emergency, so can't be helped.
Yeah, it wasn't like life or death. It was something I had to take care of over at De Anza. And so they just started their quarter today, or yesterday. So it was like I either had to take care of it then or there would have been some big problems. So thank you all for understanding. That's not the norm for me. I promise. Yes, we are. So somebody just asked in chat, so we're on Tropical Storm Beta. Yeah, no, last week we just blitzed through names, and yeah, now we are out of tropical storm names in the Atlantic, so we have to use Greek alphabet now. My question is, I don't think this is going to happen, but what would happen if we actually ran out of Greek alphabet letters? The chances of that happening are zero, but I wonder what would happen if that was the case. All right, the clock just changed to 9, so I'm going to get started. I know people trickle in, not a problem with that, but let's get started. So today is one of my favorite days of the year. And the reason why is because today marks the beginning of astronomical fall. And I don't know about you, but after 3 months of hot, dry, fiery weather, I'm ready for fall, especially this year. That being said, something I love to ask my friends and also I love to ask my students, and I thought this would be appropriate because today is the first day of fall. What are some of your favorite things about fall? And if you hate fall, you can say that too. That I'm not going to take that personally. Let me plop the link to answer this warm-up question here in chat. I know people are trickling in, so I'll post it a few more times. But go ahead and take a stab at that. Share what some of your favorite things about fall are, and then we will jump in a few minutes and talk about one of my favorite topics of the entire quarter. Let's see what people are saying. All right, a few people have just signed on, so let me plop that again in chat. All right, take another minute or two. I'm over here looking at the responses and I'm loving them. All right, it looks like there's a few people who still need to answer, but I'm going to switch over and just take a look at some of the main responses that I'm seeing on here. So I always love asking my friends this question, so it's kind of fun to be able to ask all of you as well, and also just kind of sort of warm up for the day. So let's see here. It's never too hot or too cold. I love that. I love the color of leaves changing. Halloween and Thanksgiving. The changing of the weather and trees. The weather. Halloween and Thanksgiving, yes. I really look forward to the holidays this time of year. I mean, Thanksgiving is my favorite holiday. I don't know how much COVID is going to wreck that this year, but figure it out. Let's see here. The colors. Football. A lot of people are excited for football. More chances to wear sweaters. The cooler weather. Pumpkin spice lattes. I have what I call the poor person's pumpkin spice latte. It's a cold brew with pumpkin sauce added to it. I love that. Let's see here. Get to wear warm clothes without dying from heat stroke. The fall colors. The holiday season is almost near. There's a chance for potential rainfall. That's something I'm looking forward to, is that first rain of the year. The weather, the temperature is perfect. So let's see here. Halloween. The color scheme. The colors, the holidays. This is great. So the fall weather, I can dress the way I want. I love boots, yay boots, yes. Starts to cool down, cold weather, drinking hot drinks, ready to have some cold weather. The weather, the food, the holidays, the time change, it starts to get dark earlier, the chill vibe, the leaves, and Halloween. A few more people have signed on, so let me paste this one more time for them. You know, one of the questions I should have asked is, have you noticed how climate change has actually changed fall? I can remember growing up, and I'm 35, so that's somewhat ancient history, but not super ancient history. I can remember by the time you got into October, you would get that first cold front and that first rain, and it would start to really feel like fall. I noticed that that usually doesn't come until November now. Seems like that fall weather comes really late now. And One piece of bad news I guess I'll bear to all of you is the forecast for this weekend is just terrible. The high temperature forecast on Sunday is 100 here. I'm just so like over that. But that's okay. It won't be long before we really switch over to that cooler weather, and it won't come back for a while. Yeah, this next week is going to be pretty bad. Yeah, it's not going to be good. And the thing that scares me is we're also getting into that time where we're usually kind of more in prime time for fire season. If you've noticed the last few years, fires here in California typically happen in October and November. This year we had it earlier, and it's been much more severe. So how do these things relate to climate change? Well, there's a few possibilities there. One of the biggest ones is the idea that as the world is getting warmer, that's actually disrupting the overall flow of the atmosphere. When you throw more heat into a system, that disrupts the system. That basically changes the way that the system functions. And that sort of segues pretty well into what we're talking about today. Today is all about heat. All about heat. So that's what we're talking about today. We are going all about heat. So let me jump in and let's do it. Let's talk about heat. Okay. So let me click this little button right here. So here we go. So before we can even start talking about heat, we need to start talking about the idea of temperature. Now, when you think about temperature, oftentimes you think about how hot or cold something is. That's a really typical definition of temperature. But believe it or not, there is a much more scientific, much more molecular definition of temperature. So think about this right now. The shirt that you're wearing, the hairs on your head, the seat that you're sitting on, the clothes that you're wearing, the desk in front of you, the computer in front of you, and everything around you is made up of trillions and trillions and trillions of these tiny little objects called molecules. And these molecules actually wiggle around. They don't stay in place. They actually wiggle around. And it's that the speed of that wiggling, the amount of wiggling that's happening, that actually defines an object's temperature. So when we talk about the temperature of an object, we're actually talking about the average kinetic motion of that object's molecules. Or put more in layman's terms, the speed of the molecules. So when we talk about temperature, we are talking about the speed of an object's molecules. And there's a pretty direct relationship between the speed of the molecules and the temperature. Warm objects, such as a hot cup of coffee, such as a hot light bulb, such as anything like that, has fast-moving molecules. Molecules that are just zooming around really fast. On the other hand, colder objects, like my iced coffee here, has slower moving molecules. The molecules are moving a lot slower. So, cold object, hot object. Cold object, hot object. Okay, that being said, that kind of begs an idea. So, okay, Terrence, the speed of an object's molecules defines its temperature. What happens if the molecules aren't moving at all? Well, we call that absolute zero. So if you notice on our temperature scale here in the United States, the Fahrenheit scale, you can actually go below zero. Temperatures of -10, -20, -30 are not uncommon in parts of the United States during the wintertime. That's not uncommon. It's also true in Celsius. In the Celsius scale, that's the scale that pretty much everybody else uses, a negative temperature is simply a temperature below which water freezes. So water freezes at 0, and anything colder than 0 is just below freezing. But absolute 0, this is a temperature that you cannot go lower than. At this temperature, there is 0 molecular motion. Now, here's the crazy thing. This is more of a theoretical concept than something we've actually achieved. We have gotten to within a billionth of a degree away from absolute 0, but we have never achieved absolute 0 ever. We have never achieved absolute 0 ever. So once again, just to review this concept, a colder object has slower moving molecules. A warmer object has faster moving molecules. Or if you're a jokester like me, I know my jokes suck, but at the same time, if you are a jokester like me, you can think of it like this. In a warm object, you have molecules that are going by really fast, they're bumping into each other, they're flying away from each other, they're moving all around, hot and crazy. On the other hand, when you have a cold object, its molecules are drifting by, they're waving hello to each other, some of them stick together. That's actually what's called a phase change. But they stick together, they fall in love, they get married, they start having kids, you know, American dream, house with a white picket fence, and so on, living the American dream there. Somebody had just asked in chat, what is the temperature for absolute 0? I'm glad you asked, because that is actually where we're going to start out today. I wanted to start out by talking about temperature scales. So here in the United States, we use what's called the Fahrenheit temperature scale. And us and like 2 other countries in the world use the Fahrenheit scale. And the Fahrenheit scale is actually the oldest temperature scale of these 3. It was the first one ever designed. It was designed by a gentleman named Daniel Fahrenheit. And what he wanted to do was he wanted to use these 2 markers for 0 and 100. For 0, he used this icy, briny mixture, and he tried to get it as cold as possible. If you actually throw salt into ice water, that actually causes the temperature to decrease. Why is a little bit beyond the scope of this class, but if you ever wanted to get a beer cold really fast, dunk it in some salt water. It has to be really salty, and there has to be a lot of ice in it. But it's pretty cool. You can get a beer cold like that. Well, he said that is going to be his 0. The coldest temperature he could get that was 0. And then the warmest temperature, or the 100 degree mark, was body temperature. He said, okay, body temperature is going to be 100. Now, obviously, when he developed the scale, this was actually a long, long time ago before we had well-calibrated instruments. So he was actually off by 1.4 degrees Fahrenheit. We'll forgive him. So that's the Fahrenheit scale. The Celsius scale is pretty much used everywhere else in the world. And the Celsius scale was based on the freezing and boiling points of water. So the freezing point was labeled as 0, and the boiling point was labeled as 100 degrees Celsius. So that was the Celsius scale. And Anders Celsius, the gentleman who invented the Celsius scale, came about 50-ish years after Daniel Fahrenheit. But neither of these scales were actually very useful in thermodynamics. So a new scale was created later by another gentleman named Lord Kelvin. And Lord Kelvin came up with a 3rd scale called the Kelvin scale. And the Kelvin scale was based completely on absolute 0. based completely on absolute zero. And his scale was basically the same as the Celsius scale, but it was just shifted to where zero would be absolute zero. Just in case, just to answer the question that somebody asked earlier, in Fahrenheit, absolute zero, absolute zero is approximately negative 459 degrees Fahrenheit. Negative 459 degrees Fahrenheit. And in Celsius, it's approximately negative 273.15 degrees Celsius. Sorry for my terrible penmanship there, but that was absolute zero in Fahrenheit and Celsius. Very, very, very cold. Very, very cold. More than 300 degrees colder than the lowest temperature we've ever gotten to here on Earth. So yeah, nothing can survive that. So that is the Kelvin scale. One interesting fact about the Kelvin scale is that unlike the Fahrenheit and Celsius scale, we don't use a degree symbol, or we don't say degrees in Kelvin. So we don't say 180 degrees Kelvin. Instead, we would just say 180 Kelvin. Now in this class, if you say 180 degrees Kelvin, I don't mind. But just keep in mind, if you happen to go out on a date with a climate scientist, a chemist, a physicist, and you say, wow, it must be 350 degrees Kelvin right now, and they throw their napkin down, get up and walk out, that's why. Hopefully that never happens. That'd be kind of a lame thing to walk out on, but just a little laugh. But so each one of these temperature scales, that 0 and that 100, mean very different things. In the Fahrenheit scale, 0 is very, very cold. 100 is very, very hot. In the Celsius scale, 0 is fairly cold. You know, you're going to want to wear a jacket and boots and, you know, try to keep yourself nice and warm. That's about it, though. On the other hand, 100 degrees Celsius, that's the boiling point of water. You're going to die. That's dead. And then in the Kelvin scale, 0 Kelvin, absolute 0, nothing's moving there, nothing's living there, dead. And 100 Kelvin is also very, very cold, also dead. All right, so one of the things that I always want all of my meteorology students to be able to do, just on the back of an envelope or just have a little bit of comfort with doing this, is converting temperatures from one unit to another. This is important because there will be times in this class where I will explain something in Fahrenheit and we need to convert it to Celsius, or I'll explain something in Celsius and we need to convert it to Fahrenheit. And so being able to convert temperatures from one to another is pretty important. Now here's the good news though. The good news is that I won't make you memorize these formulas. I think there's way more use for your brain space. I will give them to you. That being said, here's how they work. So if I give you a temperature in Celsius and I wanted you to convert it to Fahrenheit, what you would do is you would take your Celsius temperature, multiply it by 1.8, do that first. Do what's in the parentheses first. Remember the order of operations? Please exonerate my dead Aunt Sally, or please decapitate, or sorry, no, please execute my decapitated Aunt Sally. Sorry for anybody here who has an Aunt Sally. PEMDAS, yes. You always do what's in the parentheses first. Now, once you've done that, you're then just going to add 32. And the reason why you do that is 0 degrees Celsius is 32 degrees Fahrenheit. So you're just shifting the scale. Now, that being said, incrementally speaking, if temperatures warm by 1 degree Celsius, they're warming by 1.8 degrees Fahrenheit. So there, if you're just talking about a change in temperature, you don't add the 32. Because otherwise, that's going to give you a big number that's going to be really weird. And it's not going to work out very well. All right. Somebody give me a temperature in Celsius, and I will actually do an example. Shout one out or pop it in chat. Give me a number in Celsius. Oh, whoops.
20.
Okay, let's see here what somebody said in chats. I heard 20. 42, the meaning of life. 71. 35. That was a reference to Hitchhiker's Guide to the Galaxy, by the way. So let me start with 42. So let's do 42. Okay. So if our temperature in Celsius is 42 degrees Celsius, to convert it to Fahrenheit, I would take my temperature and multiply it by 1.8 and then add 32. So here you can totally use a calculator. So let me pull mine out right here. Cell phone calculator. Oh, let me get rid of that. 1.8 times 42 is 75.6. 75.6. That 5 looks horrible, but plus 32. So 75.6 plus 32 is going to be 107.6. (107.6 degrees Fahrenheit). Okay, now let me do the one that was shouted out. I did one from chat. I'll do one that was shouted out now. So let's say we have a temperature of 20. To convert that to Fahrenheit, we would multiply 20 by 1.8. Oops. And add 32. So 1.8 times 20 is 36. (36 plus 32 equals 68 degrees Fahrenheit. So that's how you convert Celsius to Fahrenheit. Now to convert Fahrenheit to Celsius, you literally just do the exact reverse of what you just did. So when you converted Celsius to Fahrenheit, you multiplied by 1.8 and then you added 32. Well, we're going to start with our Fahrenheit temperature. Whoops, that is a typo right there. It's always one. We're going to start with our temperature in Fahrenheit. We're going to subtract 32. That's the first thing we're going to do. We're not going to do anything else first. And then once we have that number, we then divide by 1.8. So I will take 71, which was mentioned in chat, 71 degrees Fahrenheit. And then to convert that to Celsius, I will subtract 32. And then whatever I get, I'll divide by 1.8. Okay, so 71 minus 32 is 39. I did that in my head. I counted my fingers and my toes. Let me just make sure. Yep, it's 39. So that is 39. And then 39 divided by 1.8 is 21.6666666666666666666667. So 21.6666666 and so on. Now, for the purpose of this class, anytime you do a calculation, I'm fine with you just rounding to the nearest 2 decimal places. So this would actually be 21.67 degrees Celsius. 21.67 degrees Celsius. And then finally, to convert from Celsius to Kelvin, all you do is you take your Celsius temperature and you add 273.15 to it. So if I were to take this number and convert it to Kelvin, I would 21.67. To convert that to Kelvin, I would take that 21.67 and I would add 273.15. Then once again, I'm just going to count with my fingers and my toes. That gives me 294.82 Kelvin. So 294.82 Kelvin. And then to convert from Kelvin back to Celsius, you just subtract 273.15. All right, so what I wanted to do for the next 10 minutes, before I really start talking about heat, is I want to give you a chance to actually do a few of these conversions. So in chat, whoops, I'll actually keep this page up because this one actually has all of the formulas on it. What I'm linking right now is a new Google form. And on this Google form, I'm going to have you determine which of these 2 temperatures is warmer. So on this next slide, I have the 5 problems that you're going to do. So for each one of these, you're going to determine which one is larger. Now, if this was being done in class, on campus, and you're handing it in, I would ask you to show your work, just because I want you to know how to do it. But since I don't have that luxury of being on campus, I will be grading these on accuracy. All right, so, oops, back to this. Let me put the link to this form in chat. If you would like to work on this with a group mate, send me a message and I'll put you in a breakout room. Otherwise, let's take 10 minutes to do this. It's 9:33 right now. So we will come back together at 9:43. And then I will look over and see what the general consensus was of people, and then we'll move on. let me give a quick hint. For those of you who are working with the problem where you're comparing Fahrenheit to Kelvin, what you're going to want to do is you're going to want to convert one of those two temperatures to Celsius first, and then convert it to the unit that you're looking for. All right, let's open this up and see where people are at. We've got 11 responses so far. Okay. One more hint. Neither of these, or one of these 5 questions is a trick question. One of these 5 is a trick question. Oh, yeah. Sorry. Come on. There we go. Okay, it looks like almost everybody's about done. Let's take another 2 minutes. Got roughly 5 more people who still need to submit. All right, last minute, begin wrapping up for the 4 of you who still need to submit. All right. So let's talk about these very quickly. Let's talk about these very quickly. So first one, which one is larger, 100 Fahrenheit or 100 Celsius? Well, 100 Celsius is the equivalent of 212 degrees Fahrenheit. So that is your correct answer there. For number 2, 50 degrees Fahrenheit or 15 degrees Celsius. 15 degrees Celsius is actually the equivalent of 59 degrees Fahrenheit. So once again, let me make sure. Please. 1.8 plus 32. Yep, 59 degrees Fahrenheit. 100 Fahrenheit or 300 Kelvin. 300 Kelvin is around 27 Celsius ish, which that would convert to approximately 78 degrees if I have my, I'm just doing these off the top of my head, so forgive me. So 300 minus 273.15 multiplied by 1.8 plus 32, 80. So it's actually approximately 80 degrees. And so there would be a correct answer. Down here, 0 Fahrenheit or negative 10 Celsius. Well, negative 10 Celsius would be, if I'm recalling, that would be 32 minus 18. That would be 14 degrees Fahrenheit. So that's going to be the bigger one. And then the trick question, negative 40 Fahrenheit or negative 40 Celsius. They are actually equal to each other. This actually, knowing that fact, once won somebody $250,000. I don't know if you've ever heard of the game Who Wants to Be a Millionaire? R.I.P. Regis Philbin. He was the host. Well, he actually asked that question as a $250,000 question, and the guy did the conversion right there. I remember watching it on TV. I was a little 8th grader, and I knew that, and I was like, they're the same. So you never know. I mean, you don't think you're ever going to use this, but you never know. All right. So let's actually relate all of this temperature stuff now to the main concept that we're talking about today, and that is heat. So think about everything around you right now. Everything around you right now, the chair you're sitting on, the clothes you're wearing, the desk you're sitting at, the phone or the computer you're watching this on. Think about all of those different things. Chances are all of those different things have different temperatures. Maybe slightly different, maybe very different. But all of those things have different temperatures. And that is an imbalance. And that is why heat exists. A very common prevailing theme, not just in weather, but in science in general, is Mother Nature hates imbalance. Mother Nature hates imbalance. Now, unfortunately, there's this thing called entropy, which makes it hard for Mother Nature to perfectly achieve balance. But there are ways that Mother Nature can achieve balance. Heat is one of those ways. So if you have two different objects with two different temperatures, heat will actually transfer between the two objects. And heat will move from the warmer object to the cooler object until the two have the same temperature. So I have this iced coffee right here. This is my morning addiction. And I have my hot hand right here. When I put my hot hand around my cold iced coffee, heat actually travels from my hand through the cup to the coffee. And if I kept holding on to this for hours and hours and hours, what will eventually happen is the two will eventually achieve the same temperature. And that is what we call thermal equilibrium. At thermal equilibrium, the two objects have the same temperature. And at that point, heat transfer stops. So heat moves from the warmer object to the cooler object. That transfer continues until the two objects have the same temperature. This is actually how cooking works, believe it or not. One of my favorite examples is a cold pizza. When I was in college and grad school, I was an addict of DiGiorno pizza. Nice, cheap, easy to eat. It's not delivery. Well, when you pull that pizza out of the freezer, it's cold, right? It has a temperature of below freezing. Well, if you want to cook it, you could stick it in a microwave. That actually works as well. But what a lot of people do is they stick it in an oven. Inside that oven, you have very, very warm air with a temperature of upwards of 400 degrees Fahrenheit. Well, you stick that cold pizza inside that warm oven, there is now a temperature imbalance. Heat will begin to transfer from all of that air to the pizza. So heat will transfer from all of that air to the pizza. And that process will continue and continue and continue until the two objects have the same temperature. Now, you usually don't want that to happen with your pizza. If that pizza eventually gets to the same temperature as the air, it's going to be one burnt pizza. Now, why don't you put the pizza in an oven with the air temperature, the temperature you want for the pizza? Well, the bigger the temperature difference, the faster the heat transfer occurs. So you want something that's going to be much hotter than what you actually want to achieve. But that being said, more than anything, I want you to know heat moves from warm object to cold object. And it is that heat transfer that actually allows us to do a lot of the different things in our lives, such as cooking food. And believe it or not, that's not the only thing that heat actually helps us do. Okay, now that being said, when I was touching my iced coffee, here, there was a heat transfer occurring, but it was actually only one of several types of heat transfers. So what I want to do for the remainder of class is talk a little bit about the different types of heat transfers and how they relate to our atmosphere, and ultimately how this relates to climate change. Because this actually all does wrap right back around to talking about the science behind climate change. So, once again, it all starts with heat traveling from a warmer object to a cooler object. Once the two have the same temperature, the heat transfer stops. Okay, so for the purpose of this class, there are three types of heat transfers that you need to know. You may have heard these at some point in your life. The three types of heat transfers are conduction, convection, and radiation. Conduction, convection, and radiation. I'm going to spend like 30 seconds talking about conduction and convection, and like the next 3 days talking about radiation. So I think that kind of tells you which one of these three is the most important. Now, they're all important, but conduction and convection aren't that big of a deal if we don't have radiation. So that being said, let's jump in. So here's how conduction works. Conduction is the transfer of heat one of two ways, either through direct contact. So for example, take your hand, put it on your desk. If your hand feels cold, it's because heat is actually leaving your hand and going into your desk. That is conduction. Another way that conduction can happen is through an intermediate object. So I have my iced coffee here. The thing that's cold here is the liquid inside the iced coffee, right? It's that liquid inside, it's the coffee itself that's cold. Well, when I put my hand on the cup, my hand feels cold. Why? Because heat actually travels from the liquid through the cup to my hand. In that case, the cup is acting as what is called a conductor. It is an intermediate object that moves the heat from the cold liquid to my hot hand. So an example of conduction right here. If you're trying to heat up a pointy stick, I don't know if you're trying to poke somebody with it, that'd be pretty mean. Well, what would happen is if you put this pointy stick over a flame, whoops, the flame is, or the heat is going to travel from the flame through the pointy stick to your hand. This is exactly what happens when you go to a bonfire and you're trying to make s'mores. If you're using a metal wire hanger, the heat will actually travel from the heat of the flame through that wire hanger to your hand, and it'll hurt like hell. So that's conduction. The second type of heat transfer is what's called convection. If you've ever seen bubbles of water in a pot, that's heat that's actually rising from the base of the pot up to the top. And that happens in any hot fluid. The warm stuff rises, pushing the cold stuff down. And then the cold stuff heats up and then it rises. Steam coming out of a cup of coffee, the flames rising in that bonfire are all examples of convection. Now, if this was my Met 10 class, my Introduction to Meteorology class, I would be going like super in depth over how convection works, because it's actually a very important heat transfer mechanism for creating storm systems. But really, for the purpose of this class, you just need to know convection is the vertical transfer of heat through what's called a fluid. So in convection, you need a fluid. In conduction, you needed either direct contact or an intermediate object. And the way, once again, convection works is usually something like the ground gets hot. It heats the air right above it. That air then rises, forcing cooler air to sink. It heats up, and then it rises. So that's how convection works. But really, the one that I want to talk about for the remainder of class is radiation. So let's say you're at that bonfire. You've got your stick with your marshmallow on it. You have it over the flame. And let's say the stick you have is a really good insulator, meaning it doesn't transfer heat well. So your hand's not burning. You notice all the flames shooting up, that's convection. But you're not on top of the fire. Instead, you're sitting maybe 10 feet away from the fire. And you still feel heat coming off of the fire, right? If you're 10 feet away from the fire, you still feel that heat. Keeps you nice and warm. That heat that you're feeling coming off of the bonfire is a third type of heat transfer called radiation. Now, I know when you hear the word radiation, a lot of people think of Chernobyl or Fukushima or nuclear bombs. That's one type of radiation. But guess what? If you're using a Wi-Fi signal right now, that's radiation. If you're using a cell phone, the signal in your cell phone is radiation. If you can see colors, those colors are different beams of radiation. So radiation is actually all around us. And in fact, I'm going to tell you in a few moments a few very, very key things about radiation. Now, all of that being said, the biggest bonfire known to man, the one that gives Earth all of its heat, the sun. The sun is where we get all of our heat from. In fact, over 99% of the heat that is present on Earth's surface comes from the sun. Including the foods you eat, including the electricity powering your computer. At some point, 99% of that energy started out with the sun. It's kind of crazy. Even the fossil fuels that we're going to be talking about in the next couple of weeks actually all started with energy from the sun. So pretty crazy stuff. So over 99% of the heat that fuels energy here on Earth's surface comes from the sun. And the way that the sun heats the Earth up is via a process called electromagnetic radiation. I know what you're thinking. That sounds like a crazy term. Electromagnetic. It sounds very over the top. That's okay. I failed my electricity and magnetism class when I first took it. I got an A the second time, so don't worry. Sometimes that happens. But electromagnetic radiation are basically beams of energy. And these energetic beams contain both electricity and magnetism in them. Hence, we call them electromagnetic. Well, the good news is all of this energy that comes from the sun is harvestable. We can actually harness this energy. And we do that using solar panels. So solar panels are actually a way that we can harvest a lot of the sun's energy and use it to fuel things like my computer, the lights I have on in this room. We can actually use that energy to power our everyday life. So it is actually crucial. Now that being said, let's talk a little bit about this radiation. I have a couple of really important things to say about it in the next 9 minutes, and then next time we're going to talk a lot more about what Earth does with this radiation. So here we go. Radiation is the transfer of energy in the form of those electromagnetic waves I was talking about. Well, the cool thing about radiation is, unlike conduction and convection, radiation doesn't need anything to travel. Radiation does not need any object to travel through. So when talking about conduction, in order for the in order for the heat from my hand to travel to this cold liquid inside this cup, energy has to travel through the cup itself. In order for the heat transfer to occur, heat needs to travel from my hand through the cup to the cold iced coffee. Radiation doesn't need that. For convection, you need a fluid. You need some kind of gas or some kind of liquid for convection to work. Well, for radiation, you need nothing. You need nothing. Radiation can also travel through many different objects. So for example, if you have a window in your room right now, that window is a medium. What I mean by that is that sunlight is traveling through that window into your bedroom. But in some cases, radiation doesn't need anything. Radiation can travel through empty space, or what we call a vacuum. That is how radiation is able to make that 93 million mile journey from the sun to the Earth. It's able to travel through empty space. But it can travel through other objects as well. If you're getting a Wi-Fi signal in your room, it's because the radiation that signal is made up of can travel through those walls. The same thing works for radio waves, television waves. Any of those things can travel through your walls. But they don't need anything to actually travel through them. So that's why radiation is so important. Now that being said, I just mentioned cell phone waves, I just mentioned visible light, I just mentioned AM radio waves. Well, what determines the type of radiation? Well, it's one big thing, and that big thing is what is called wavelength. The wavelength of a beam of radiation tells us everything we need to know about the radiation. The wavelength tells us everything. And in fact, it is the wavelength that dictates the frequency of the radiation and the energy emitted by the radiation. It is the wavelength that dictates those other two things. So what is the wavelength? Well, if we were to zoom in and actually see a visual representation of a beam of radiation, here's what it would look like. It would look like a wave that goes up, peaks, goes down, bottoms out, goes up again, peaks, goes down, and bottoms out. Well, the wavelength of a beam of radiation is simply the distance between two consecutive peaks. The wavelength of a beam of radiation is simply the distance between two consecutive peaks. Now, that being said, when we talk about distance, what are some of the units that we usually measure distance in? What are some of the units we usually measure distance in? All right, a few people are speaking up in chat. Miles, so 2 people saying miles. Okay, centimeters, meters. So I've heard miles, centimeters, meters, feet, kilometers, inches. So I've got a pretty good comprehensive list here. Well, here's the crazy thing. Most radiation, the wavelength is too short for those units to work. So I have to introduce a new unit. And the new unit I'm going to introduce is what is called the micrometer, also known as the micron. And it has this weird symbol. It's actually the Greek letter mu, and it just means micro. So 1 micrometer is actually the equivalent of 1/1,000,000th of a meter. So take a meter, it's about that long, maybe a little bit more, cut it up into 1,000,000 equal sized pieces. That's a micrometer. A sheet of paper. Trying to see if I have a sheet of paper here. I have this little loyalty card sticker thingy. The thickness of this little sheet of paper is measured in micrometers, and actually in multiple micrometers. So all of that to say, a micrometer is really, really tiny. Well, it is this wavelength that determines everything we need to know about radiation. And in fact, frequency and energy are inversely related to this wavelength. What I mean by that is the longer the wavelength, the lower the frequency and the less energetic. The reason why that is that those peaks are now spread out over a larger area. That means they're less frequent and therefore less energetic. They're less frequent and therefore less energetic. The opposite is true as well. The shorter the wavelength, the more energetic and the more frequent this radiation is. But everything from ultraviolet radiation, X-ray radiation, gamma ray radiation, visible light, infrared radiation are all determined solely by the wavelength. Let me end class by telling you one very cool fact. Look around the room right now that you're sitting in and ask yourself, what is emitting radiation right now? Well, there is actually an interesting fact. I call it a law more jokingly than anything. I like to call it Oprah's law. I'll explain why next. Well, no, I can explain why right now. I've got 30 more seconds. The law states that anything with a temperature above absolute zero emits radiation. Think about that really quickly. Think about what around you right now has a temperature above absolute zero. Guess what? The chair you're sitting on emits radiation. The desk that your computer is on right now emits radiation. The clothes you are wearing emit radiation. And you emit radiation, 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 and you emit radiation. Everybody emits radiation. So when people ask you, what did you learn in your global warming class today? You could tell them, my teacher told me that I'm radiant, that I emit radiation. Now, that's the good news. I do have some bad news, and the bad news is even though you're radiant, you are not glowing. Why? We'll talk about that next time. All right, everybody, that's it for today. Have an awesome day. It should be beautiful today and tomorrow, and then the heat wave comes. Have an awesome day, everybody. Thank you all for being here, and I'll see you all on Thursday.
Thank you.
Thank you.
Bye.
Thank you, Professor.
Thank you.
Thank you.
Take care, everybody.
Professor,
How can I help?
can I say the warm-up question again?
Sure. Oh, what is your question?
Oh, it's because I came in a little bit after the warm-up question.
Oh, okay. I thought you said
Yeah.
homework question. Okay.
No,
Yes,
yeah.
I can get you that.
Thank you.
Here we go. Let me give me 1 second here. I just need to copy this back down.
For the trick question, I actually put even, and then I was like, I don't know, so I put
Oh, that's
negative
fine.
40. I was
Oh
like,
no!
yeah, I actually typed in even, and then I was like, nah, I'll put negative 40 Celsius.
Oh no!
Yeah.
Okay, so here is the warm-up question again. Right there. So if you click on that, that should get you right in there.
All right, thank you.
All good? All right. Anybody else have any questions, comments, concerns, anything else I can help out with right now?
I do have a. Oh, sorry, you can go.
No, not a problem.
Oh, okay. Oh, where is it? Okay. I was just wondering how your quiz and stuff work. Like, you don't do retake quizzes or anything, right?
I dropped the lowest quiz.
Okay. Okay.
I dropped the lowest quiz. So if you miss a quiz, that would be your drop.
Okay. So I did take a quiz. I only did it one time though, because it was pretty rushed on my end, but
Oh,
I
okay.
wasn't able to take it the second time, so the score is like pretty low on it. So I was just concerned about it.
Oh, okay. Well, the good news is that if you do better on the other quizzes, that would be your drop quiz. The other good news is that in the next few weeks, I'm going to be assigning some extra credit.
Oh, okay, good. Thank you.
Absolutely.
All right, have a good one.
You
Bye-bye.
too.
Hello. The other week we went over a question on the first quiz we did, and we found that one of the key answers was wrong. And I wonder if I was wondering if you were going to change that, or if we're waiting for someone.
I thought I already corrected that. I
Oh,
do remember
okay. I
that.
just didn't.
Let me double check just to make sure.
All right. Thank you.
Yeah, of course. Let me double check that real quick. So let's see here. This is Met 12. Quiz number 1. And let's see what we have here. Okay. Oh yeah, I think I remember this. Wait, I thought I changed that. I don't know why Canvas reverted it. Okay, well, let me fix that now. Canvas sometimes makes me click save like 4 times. So I could have sworn I changed it, but
Fine.
thank you for letting me know. I have changed it now, so now it's good.
All right. Thank you so much. Have a nice day.
Absolutely, you too. Anybody else I can help out with real quick? Yes, no, maybe so. Well, if you can hear me and you have any questions, please don't hesitate to email me or stop by my office hour. Otherwise, have an awesome day.